Hello everyone, so welcome to the virtual lab of heat transfer by natural convection. So this is the URL link which is provided at this particular website. So when you click this particular website, then you will first find theory option, right? So here you are having two aims. The first aim is to determine overall heat transfer coefficient at the surface of a given vertical metal rod, or you can say cylinder, by natural convection, and ultimately you need to determine value of Nusslet number. So this is our apparatus. So this apparatus consists of a metal rod, and inside the metal rod you are having heater. So by varying the voltage and ampere, you can vary the heat supplied to this heater, and this heater will actually used to heat this metal rod, right? And in order to measure the temperature of this metal rod, you are having four thermocouples. So this thermocouples T2, T3, T4 and T5 are used to measure temperature of the cylinder, whereas thermocouple T1 and T6 are used to measure temperature of the surrounding air, right? So this is our typical apparatus, which is you can say mounted inside the vertical duct, which is made of wooden, right? So wood is having low thermal conductivity, so it will not play any role in terms of altering the heat transfer coefficient of this particular phenomena. So this is the typical apparatus, and then you are having theory where we are actually interested to calculate Nusselt number, which is a ratio of heat transfer by convection to the heat transfer by conduction, right? So this is the equation which you have studied in your UG level, and you know that this K is nothing but thermal conductivity of the air, right? So this K is thermal conductivity of the air, and L, which is the characteristics length, is nothing but length of this vertical cylinder. Okay, so let us straight away go to our simulator, right? So before going to that simulator part, you can also go through this particular steps where you all the steps are explained in details, and then you can also go through the self evaluation in order to check your level of understanding for this particular topic. And then you can straight away go to the simulator part. So this simulator, if you open this particular URL in Internet Explorer, then you should be able to see this kind of test setup. So this is our test setup, right? So this is our vertical cylinder, which is mounted with 6 number of thermocouples. So this thermocouples T2, T3, T4 and T5 will be used to measure temperature of this metal rod, whereas thermocouple T1 and T6 will be used to measure temperature of the air. And if you want to see the position of your heater, then you can click on this show cross section, and you will be see that the heater is mounted somewhere around here, right? So when you measure your temperature of all the thermocouple, then you would expect that temperature of this thermocouple T3 and T4 will be higher as compared to other thermocouples, right? So here you are having voltage as well as ampere meter. So by varying, by using this knob, you can alter the heat supply to this metal rod, right? So let us go through all the tabs. So here you are having option of choosing material. So these materials will be material of this metal rod. So here you are having option of aluminum, copper, iron, silver and steel. So let us start with aluminum only. And here you can also alter the size of the wooden box. If you recall this particular apparatus, then this is actually mounted inside the wooden box, right? So the default value is 7.5 centimeter, but you can alter the size between 5 to 10 centimeters. So this is the side of wooden box. Similarly, you can also vary the height of wooden box. So default value is also 75 centimeter, but you can alter if you are interested to check the effect of this particular thing on your heat transfer coefficient. Similarly, you can also vary diameter of the cylinder. So the default value is 7 centimeter, but you can play between 4 to 10 centimeter. Similarly, this is the length of this particular cylinder. The default value is 55 centimeter, and you can vary between 50 to 60 centimeter. And you can also play with the thickness of the cylinder, right? So the default value is 0.2 centimeter, and the lower limit is 0.1 and upper limit is 0.3 centimeter. So for the time being, let us consider the default values of all this geometrical parameter, right? So first let us set voltage in ampere, right? So if I click here, then you will get 100 volt and 0.2 ampere. If again you will click on this side, you will get some other values, right? So that value will be appearing in this particular window when you click the power button on. Okay, so let me click this power button on. So when I click here power on, then you will find that for this particular setup the voltage is 110 and amperage is 0.3. Okay, and here you will see that this timer is already started. So the moment this timer reaches this 20 minute, that means you have reached the steady state condition. So this is the setting which is provided by this virtual lab, but in reality you may get different time, right? So now this timer has stopped, so you have reached the steady state condition. Now it's time to measure temperature of all the thermocouples, that is T1, T2, T3, T4, T5 and T6, and this can be measured by using this particular knob button. Okay, so here so this 30 is actually temperature of your thermocouple 1. Okay, so let me create one Excel file and we'll store those data, and then I can able to explain how you can calculate the heat transfer coefficient. So this is the thermocouple 1. Okay, and the temperature of thermocouple 1 is 30, and then let me also copy this thing as a T2, T3, T4, T5 and T6, right? So T2, then you are having T3, T4, T5 and T6, right? And we know that this thermocouple T1 and T6 are actually used to measure temperature of the air, whereas thermocouple T2, T3, T4 and T5 will be used to measure temperature of this metal rod. Okay, so you should be aware of that thing. And in order to not have any confusion, let me uh, replace T1 from this position to this position. Okay, so that I can understand that this two thermocouples belongs to temperature of the air, whereas this this four thermocouples belongs to temperature of the metal cylinder rod. Okay, so let me now store those data, right? So here I have to remove this part. Okay, right. So temperature of thermocouple 1 is 30, then I'll click on 2, so I'll get temperature of thermocouple as T2 as a 58.33 degrees Celsius. Then if I'll again click here, then I'll get 64.33, 64.33. And if I'll again click right, so this is actually T3, right? We have already noted down or what? So now I'm getting 66.33, which is a temperature of thermocouple 4. So 66.33, and then again I'll click, then I'll get 60.33, right? So 60.33, and finally if I'll click the last button, then I'll get T6 as a 36 degrees Celsius. Okay, so this four thermocouples belongs to temperature of the metal rod, and these two thermocouples belongs to temperature of air. Okay, so let me average of this four thermocouple. So you can do simply by first summing these four thermocouples and then divided by 4. Similarly, you can also perform the same thing here by summing up these two temperatures and you can divide by 2. So you'll get temperature of this two, average temperature of this air as well as metal cylinder rod, right? So you know this temperature of the air, and then by looking at this voltage and ampere you can calculate Q, which is nothing but V into I. So V is 110 and I is 0.3, so you'll get Q as a 33 watt. Okay, and if you talk about the surface area A, then surface area is nothing but pi dl, right, where d is the diameter of the cylinder, L is the length of the cylinder. So let me also calculate here itself. So pi into diameter of the cylinder is 7 centimeters, so you can put here as a 7 divided by 100, because we also have to convert in meter, right? So this is 7 by 100, which is the diameter of the cylinder, and length of the cylinder is 55 centimeter, so that will be 55 divided by 100. So you'll get surface area as a 0.12095 meter square, right? And you know that your H is nothing but Q divided by A delta T, right? So what is your Q? Q is here, then divided by area, area is here, and your delta T is nothing but temperature of the metal cylinder minus temperature of the air. Okay, so once you perform this calculation, you will get heat transfer coefficient H as a 9.30232, and the unit is obviously watt per meter Kelvin, and then sorry, watt per meter square Kelvin, right? And if you want to calculate Nusslet number, then Nusslet number is nothing but HLC by KF, where H is heat transfer coefficient and LC is the length of this metal rod, which is given as a 55 centimeter, and you need to convert that into meters. So that's why you'll have 55 divided by 100, and that should be divided by KF, and KF is a air, thermal conductivity of the air, right? So I think it is already mentioned here. You need to take as a 0.024, right? So it is already mentioned, so you can take 0.024 and you will get your Nusslet number as 213.1782. And if you want to verify your result, right, I think we missed that part. Let me see. Yeah, I think we have missed that part, so I need to again run this simulator, but it will hardly take some hardly a fraction of a minute, right? So let me again click this button. So we are performing the same simulation with the same parameters. We are not changing anything, so we are expecting to get the same temperature data as we got earlier, right? So let us wait for the steady state condition to reach. The moment we get steady state condition, we will verify our data, right? So we have reached our steady state condition, and if you want to verify your result, then you can click at this particular mark, and then you will get your result as a heat transfer coefficient as a 9.3059, right? We are also getting the similar value, 9.30 something. And if you talk about this Nusslet number, then here it is mentioned as a 213.26, and I am also getting the similar value. So by this way we can verify our calculation also. Okay, so this is the tentative process which you need to perform, right? So once you perform one set of experiment, then you can also vary material of the metal rod, and you can perform the similar calculation or simulation with the same, you can say, power rating. So this is one set of experiment you can have. Then you can have the same material, but you can vary different power. Okay, so if you change higher power, then you will get some different sets of temperature reading, right? And accordingly you can calculate your heat transfer coefficient as well as Nusslet number. So that is your second set of question. And then you can also vary thickness, or you can say length of this cylinder, and you can also perform the similar kind of experiment, so that you can have parametric studies to check what is the effect of surface area. Basically, when you are changing length or diameter, you are actually changing surface area, which is nothing but pi dl, right? So by changing the diameter or length, you can have a effect of surface area on heat transfer coefficient. So that could be another parametric study. And then if you are still interested, you can also vary the change of wooden box, and accordingly you can change the dimension of your cylinder, right? So I think you can have a three sets of, effectively you can have a three set of comparison. One is the effect of metal rod on heat transfer coefficient, and then you are having effect of power input on heat transfer coefficient, and then you are also having effect of surface area on heat transfer coefficient, right? So for the first set of question, I would suggest you to perform this kind of calculation, so that you can have better, you can say, insight what's going on inside the simulation, or we can say this convection. But once you get this result, then you don't have to perform this calculation again and again. You just use this show result button, and you can straight away go to the next set of lab. Okay, so I hope this will be very useful to you, right? So just practice with this thing. And one more thing, if you open this particular tab on your Google Chrome, then you may find this kind of option that content on this page requires a newer version of Adobe Flash Player. So try to update your Adobe Flash Player in this Google Chrome or Mozilla, whatever you are using. But if this problem still exists, then I would suggest you to open this particular website in this Internet Explorer, right? So I'm hoping that you will be able to see this kind of setup and you will not face that problem. Okay, so with that, I'll end the explanation of this lab, and I hope you will get something useful from this video.